The universe is vast beyond comprehension, stretching across distances so immense that light itself takes billions of years to traverse them. Within this cosmic expanse exist phenomena so extreme, so violent, and so fundamentally alien to human experience that they challenge our very ability to understand reality. These are places where the laws of physics, as we know them, break down, where matter behaves in ways that seem impossible, and where the fabric of spacetime itself becomes twisted into configurations that defy imagination. We live on a relatively peaceful world, orbiting a stable star in a quiet corner of our galaxy. The Earth shields us from the harsh radiation of space. Our atmosphere protects us from meteorites, and our magnetic field deflects the solar wind. We experience gravity at a comfortable 1 g, temperatures that allow water to exist in all three states, and an environment that has remained stable enough for life to flourish for billions of years. But venture beyond our protective bubble, and the universe reveals itself to be a place of extraordinary danger and mind-bending extremes. Consider for a moment what happens when stars die. Our sun will one day exhaust its nuclear fuel, swelling into a red giant that will engulf the inner planets before collapsing into a white dwarf. But this relatively gentle death is reserved only for stars of modest mass. More massive stars meet far more violent ends, and in doing so, they create some of the most terrifying objects in the cosmos. When a star perhaps 20 or 30 times the mass of our sun reaches the end of its life, its core collapses in a fraction of a second. The outer layers rebound in a catastrophic explosion called a supernova, briefly outshining entire galaxies. The energy released in this explosion is almost incomprehensible. In a few seconds, a supernova generates more energy than our sun will produce in its entire 10 billion year lifetime. The light from such an explosion, if it occurred close enough, could sterilize the Earth from hundreds of light years away. But the explosion itself is only the beginning of the story. What remains after the star's outer layers have been blasted into space is something far stranger and more dangerous than the star that preceded it. If the core that remains is between about 1.4 and 3 solar masses, the crushing force of gravity compresses it into a neutron star. If the core is more massive than about 3 solar masses, nothing in the universe can stop its collapse, and it becomes a black hole. Let us first explore neutron stars, objects so dense that they make even the most extreme conditions on Earth seem trivial by comparison. A neutron star packs roughly 1.5 times the mass of the Sun into a sphere only about 20 kilometers across. To put this in perspective, if you could take a teaspoon of neutron star material and bring it to Earth, it would weigh about 1 billion tons. The gravity at the surface of a neutron star is approximately 200 billion times stronger than Earth's gravity. Standing on the surface of a neutron star, if such a thing were possible, you would be instantly crushed into a layer of atoms just a few atoms thick. Your body would cease to exist as anything resembling its original form, compressed into a smear of matter on its surface, harder than any material that exists in normal circumstances. The neutron star's gravity would be so intense that it would compress your remains with such force that the very atoms of your body would be crushed together, electrons forced into protons to create neutrons, the same particles that give these stars their name. The surface of a neutron star is thought to be composed of iron nuclei arranged in a crystalline lattice, forming a crust billions of times stronger than steel. Beneath this crust lies a superfluid sea of neutrons, flowing without friction or viscosity, in ways that seem to violate our everyday understanding of how matter behaves. Deeper still, the pressure and density become so extreme that nuclear matter exists in exotic states that we can barely theorize about, let alone observe directly. But neutron stars possess another characteristic that makes them even more dangerous than their density alone would suggest. They spin, and they spin fast. Some neutron stars rotate hundreds of times per second, their surfaces moving at significant fractions of the speed of light. This rotation, combined with powerful magnetic fields, creates what we call pulsars. These are neutron stars that emit beams of radio waves from their magnetic poles, and as the star rotates, these beams sweep across space like a cosmic lighthouse. Some neutron stars, called magnetars, possess magnetic fields so powerful that they represent another category of cosmic terror entirely. The magnetic field of a magnetar can reach 10 to the 15th Gauss, about 1,000 trillion times stronger than Earth's magnetic field, and 1,000 times stronger than a typical neutron star. This might sound like just another impressive number, but the implications are staggering. If a magnetar existed at even half the distance from Earth to the Moon, its magnetic field would be strong enough to disrupt the molecular bonds in your body. You would quite literally come apart at the atomic level. Every piece of magnetic material on Earth would be ripped from its moorings and accelerated toward the magnetar. The magnetic field would induce currents in any conductor, generating heat so intense that the oceans would boil and the atmosphere would be stripped away. Magnetars occasionally experience what are called starquakes. The crust of the neutron star, under tremendous stress from the magnetic field, suddenly cracks and shifts. This releases an enormous burst of gamma rays and X-rays. In December of 2004, a magnetar called SGR 1000, 806-20, located about 50,000 light-years from Earth, experienced such a starquake. The burst of radiation it released traveled across that vast distance and, in 1/10 of a second, delivered more energy to Earth's upper atmosphere than the Sun typically delivers in several days. This was from an event that occurred 50,000 light-years away. If such a starquake had occurred from a magnetar just 10 light-years distant, the radiation would have been intense enough to cause a mass extinction on Earth, destroying the ozone layer and exposing the surface to lethal levels of solar ultraviolet radiation for years. The burst itself would have delivered a dose of gamma radiation sufficient to kill any organism not shielded by significant amounts of rock or water. But as terrifying as neutron stars and magnetars are, they pale in comparison to what happens when a stellar core is too massive even for neutrons to resist gravity's pull. When this occurs, the collapse continues past the neutron star stage, and the object becomes a black hole. Black holes are perhaps the most famous of cosmic terrors, and for good reason. They represent the complete and total victory of gravity over all other forces in nature. Once an object crosses the event horizon of a black hole, not even light can escape. This is not merely a matter of insufficient velocity or energy. It is a fundamental property of spacetime itself. Inside the event horizon, all paths through spacetime lead inward toward the singularity at the black hole's center. The mathematics of general relativity, Einstein's theory of gravity, predict that at the center of a black hole lies a singularity, a point where density becomes infinite, and the curvature of spacetime becomes infinite. Our current theories of physics break down completely at this point. We simply do not know what happens at a singularity, because the equations that describe reality produce meaningless infinities when applied to these conditions. Approaching a black hole would be an experience unlike anything else in the universe. As you fell toward the event horizon, you would experience what physicists call spaghettification, though the technical term is tidal disruption. The gravitational force on the part of your body closer to the black hole would be enormously stronger than the force on the part farther away. This difference in gravitational pull would stretch you along the direction of fall, while compressing you perpendicular to it. For a stellar mass black hole, the kind formed from a collapsed star, perhaps 10 to 20 times the mass of the Sun, this stretching would begin well before you reach the event horizon. Your body would be pulled apart, torn into individual atoms, and those atoms themselves would eventually be ripped apart into their constituent particles. You would be transformed from a complex biological organism into a stream of elementary particles spiraling toward oblivion. For a supermassive black hole, the kind that lurks at the center of most galaxies, including our own, the experience would be different, but no less fatal. These objects contain millions, or even billions of solar masses, and their event horizons can be larger than our entire solar system. The tidal forces at the event horizon of such a massive black hole are actually quite weak compared to those of a stellar mass black hole. You could, in theory, cross the event horizon of a supermassive black hole without immediately being torn apart. But this would provide only a temporary reprieve. Once inside the event horizon, your fate is sealed. No force in the universe, no amount of thrust or energy could prevent you from reaching the singularity. You would have a finite amount of time, perhaps hours or even days for the largest supermassive black holes, but eventually, the tidal forces would intensify as you approach the singularity, and you would meet the same fate as you would falling into a smaller black hole. From the outside, however, something strange would appear to happen to you as you fell toward the event horizon. Due to the effects of gravitational time dilation, clocks run slower in stronger gravitational fields. To an outside observer watching you fall into a black hole, you would appear to slow down as you approach the event horizon, your image becoming increasingly redshifted as the light escaping from you loses energy climbing out of the gravitational well. You would appear to freeze at the event horizon, your image fading and reddening until it disappeared entirely, even though from your perspective, you would have crossed the event horizon and reached the singularity in a finite time. Black holes are not static objects. They can spin, and many of them do, some at nearly the maximum rate allowed by general relativity. A spinning black hole drags spacetime itself around with it in a phenomenon called frame dragging. Near the event horizon of a rapidly rotating black hole, space is being pulled around so violently that it becomes impossible to remain stationary, even in principle. You would be forced to move in the direction of the black hole's rotation, regardless of how much energy you expended trying to resist. Around a spinning black hole exists a region called the ergosphere, where the dragging of spacetime becomes so extreme that even light must rotate with the black hole. Within the ergosphere, it is theoretically possible to extract energy from the black hole's rotation through a process called the Penrose process. But entering the ergosphere would be extraordinarily dangerous, as the tidal forces and the violence of the twisted spacetime would pose enormous challenges. Many black holes are not quiet, isolated objects drifting through space. Instead, they actively feed on matter from their surroundings, pulling in gas, dust, and even entire stars. As matter spirals into a black hole, it forms an accretion disk, a swirling maelstrom of material heated to millions of degrees by friction and compression. These accretion disks emit tremendous amounts of radiation across the entire electromagnetic spectrum, from radio waves to X-rays and gamma rays. The environment near an actively feeding black hole is one of the most violent and energetic in the universe. Material in the accretion disk travels at significant fractions of the speed of light, colliding with other material and generating shock waves and magnetic fields of enormous strength. Powerful jets of plasma can be launched from the regions near the black hole's poles, shooting out at velocities approaching the speed of light, and extending for thousands, or even millions of light years, into intergalactic space. These jets are among the most powerful phenomena in the universe, carrying away tremendous amounts of energy and momentum from the vicinity of the black hole. If Earth were in the path of one of these jets, even from a black hole thousands of light years away, the radiation would be intense enough to sterilize our planet's surface in moments. At the centers of most large galaxies, including our own Milky Way, lurk supermassive black holes containing millions to billions of solar masses. Our galaxy's central black hole, called Sagittarius A*, contains approximately 4 million solar masses. It sits roughly 26,000 light years from Earth, a relatively safe distance that has allowed life to flourish on our world. But Sagittarius A* is currently quiescent, not actively feeding on large amounts of material. This has not always been the case. Evidence suggests that in the past, our galaxy's central black hole was much more active, and it may become active again in the future. When galaxies collide, as the Milky Way and the Andromeda Galaxy are predicted to do in about 4 billion years, the central supermassive black holes can become extremely active as they are fed enormous amounts of gas and stars, disrupted by the gravitational chaos of the merger. Some supermassive black holes power objects called quasars, the brightest sustained sources of electromagnetic radiation in the universe. A quasar is an actively feeding supermassive black hole in the early universe, surrounded by an accretion disk so luminous that it can outshine the entire galaxy containing it. The most luminous quasars emit as much energy as 1,000 trillion suns. They can be seen from billions of light years away, beacons visible across most of the observable universe. The radiation from a quasar would be lethal to any life anywhere in its host galaxy. The intense ultraviolet and X-ray emission would destroy any planetary atmospheres and sterilize surfaces. The jets of relativistic particles would flood the galaxy with deadly radiation. A galaxy hosting an active quasar is a galaxy where life as we know it cannot exist. But there exist objects even stranger than supermassive black holes at galactic centers. In the early universe, conditions may have allowed for the formation of intermediate mass black holes, objects containing hundreds to thousands of solar masses that don't fit neatly into either the stellar mass or supermassive categories. Some of these may have formed from the direct collapse of enormous clouds of primordial gas, never having been stars at all. Others may have formed from the collision and merger of many stellar mass black holes in dense star clusters. Even more exotic are the theoretical primordial black holes, objects that could have formed in the first moments after the Big Bang from density fluctuations in the early universe. These could range in mass from tiny fractions of a gram to thousands of solar masses. The smallest primordial black holes would have evaporated long ago through a process called Hawking radiation. But larger ones could still exist, scattered throughout the universe, invisible, and nearly impossible to detect unless they happen to interact gravitationally with visible matter. The concept of Hawking radiation itself reveals another disturbing aspect of black holes. According to quantum mechanics, particle-antiparticle pairs are constantly appearing and annihilating throughout empty space. Near the event horizon of a black hole, one particle of such a pair might fall into the black hole while the other escapes. From a distance, this appears as if the black hole is emitting radiation and slowly losing mass. For stellar mass and larger black holes, this process is extraordinarily slow, taking longer than the current age of the universe for even a solar mass black hole to evaporate completely. But for smaller black holes, the process accelerates dramatically. A black hole with the mass of a mountain would evaporate in about the age of the universe. As a black hole shrinks, the Hawking radiation increases in intensity. In its final moments, a small black hole would explode with the energy of millions of nuclear weapons. If a primordial black hole happened to be reaching the end of its life near Earth, the resulting blast of gamma rays and particles could pose a significant threat to our planet. Beyond black holes, the universe contains other regions where space-time itself becomes dangerously distorted. When two black holes orbit each other, they create ripples in space-time called gravitational waves. As these waves carry energy away from the system, the black holes spiral closer together, orbiting faster and faster until they finally merge in a catastrophic collision that releases more energy in gravitational waves than all the stars in the observable universe emit in light during the same period. The merger of two black holes creates a violent distortion in the fabric of space-time itself. Space stretches and compresses rhythmically as the gravitational waves pass through. For the black hole merger events we have detected so far, occurring billions of light years away, these waves are extraordinarily weak by the time they reach Earth, stretching and compressing space by less than the width of a proton over a distance of several kilometers. But imagine being near such an event. Close to a black hole merger, the gravitational waves would be powerful enough to tear apart planets, stars, and anything else in their path. Space itself would oscillate violently, stretching and compressing by significant fractions. Any object caught in this region would be shaken apart by tidal forces that change direction hundreds of times per second. Even the nuclei of atoms would be stressed by the passing waves. Neutron stars can also merge, and when they do, they create an event that combines extreme density, powerful magnetic fields, intense radiation, and the violent dynamics of colliding objects made of the densest matter in the universe. The collision of two neutron stars generates gravitational waves, just like black holes, but it also produces an electromagnetic fireworks display across the entire spectrum. When neutron stars collide, they spray matter out into space at velocities approaching the speed of light. This ejected material, compressed and heated to billions of degrees, becomes the site of rapid neutron capture nucleosynthesis, the process that creates most of the heavy elements in the universe. Gold, platinum, uranium, and most elements heavier than iron are thought to be formed primarily in neutron star mergers. The beautiful gold ring on someone's finger is made of atoms forged in one of the most violent events the universe can produce. The collision also generates a burst of gamma rays so intense that it can be detected from billions of light years away. If a neutron star merger occurred within a few thousand light years of Earth, and one of the gamma ray jets happened to point in our direction, the burst could deliver enough radiation to cause a mass extinction event, destroying the ozone layer and bathing the surface in deadly solar ultraviolet radiation for years afterward. These gamma-ray bursts represent another category of cosmic terror. They are the most luminous electromagnetic events known to occur in the universe. For a few seconds to a few minutes, a gamma-ray burst can outshine every other source of gamma rays in the observable universe combined. The energy released in the most powerful gamma-ray bursts is almost incomprehensible, equivalent to converting several solar masses worth of matter directly into energy, all released in a narrow beam in a matter of seconds. There are two main types of gamma-ray bursts. Short-duration bursts, lasting less than 2 seconds, are thought to be caused by neutron-star mergers, or the merger of a neutron star with a black hole. Long-duration bursts, lasting more than 2 seconds and sometimes continuing for minutes, are associated with a special type of supernova called a hypernova or collapsar, where an extremely massive star collapses directly into a black hole. In a collapsar event, a star perhaps 40 or 50 times the mass of the Sun reaches the end of its life. Its core collapses into a black hole, but the outer layers of the star contain so much angular momentum that they cannot fall directly in. Instead, they form an accretion disk around the newly formed black hole. The tremendous energy released as matter spirals into the black hole drives powerful jets out along the rotation axis of the system, punching through the remaining stellar envelope and erupting into space at nearly the speed of light. These jets carry with them an enormous amount of energy, focused into a narrow cone, perhaps just a few degrees wide. Within this cone, the beam of gamma rays and relativistic particles is so intense that it could be lethal to life on planets thousands of light years away. Fortunately, we only see a gamma ray burst when one of these jets happens to point directly at Earth, and the events are rare and occur in distant galaxies. But they serve as a reminder that the universe can produce directed energy weapons of cosmic scale, capable of sterilizing entire regions of a galaxy. Scientists have investigated whether gamma-ray bursts could have been responsible for mass extinctions in Earth's past. The Ordovician extinction, which occurred about 450 million years ago and wiped out roughly 85% of marine species, has been hypothesized to have been triggered by a gamma-ray burst. If a burst occurred within our galaxy at a distance of a few thousand light years, the radiation could have destroyed enough of Earth's ozone layer to expose the surface to harmful levels of ultraviolet radiation from the sun, killing off photosynthetic organisms in the oceans and on land, and disrupting the entire food chain. The threat from gamma-ray bursts highlights an uncomfortable truth about our existence in the universe. We live in a cosmic shooting gallery, where events of extraordinary violence occur regularly throughout space and time. We are protected only by distance and probability. The vast majority of these events occur so far away that they pose no threat to us. But it is not impossible that a nearby star could explode as a supernova, or that a gamma-ray burst could occur within our galaxy with its beam pointed toward Earth. Astronomers have identified several stars within a few hundred light-years of Earth that could potentially explode as supernovae in the astronomically near future, meaning within the next few million years. Betelgeuse, the red supergiant star that marks the shoulder of the constellation Orion, is perhaps the most famous example. At a distance of about 640 light-years, Betelgeuse is close enough that when it explodes, it will become as bright as the full moon in Earth's sky, visible even during the day, and remaining visible for weeks or months. However, Betelgeuse is far enough away, and its rotation axis is oriented such that it poses no significant threat to Earth. The same cannot be said for all nearby massive stars. If a supernova occurred within about 30 light-years of Earth, the blast of cosmic rays and radiation could have significant effects on our atmosphere and climate. Within about 10 light-years, a supernova could potentially cause a mass extinction. Even more concerning would be a star that could produce a gamma-ray burst. The star WR104, located about 8,000 light-years from Earth, is a Wolf-Rayet star in a binary system that could potentially produce a gamma-ray burst when it explodes. Wolf-Rayet stars are extremely massive stars that have blown off their outer hydrogen envelopes, exposing their helium and heavier element cores. They are among the most likely progenitors of long-duration gamma-ray bursts. Initial observations suggested that WR104's rotation axis might be pointed roughly toward Earth, which caused some concern. More recent observations suggest the alignment may not be as direct as initially feared, but the uncertainty remains. If WR104 were to explode as a hypernova with a gamma-ray burst pointed at Earth, even from 8,000 light-years away, the radiation could potentially cause significant damage to our ozone layer and biosphere. Beyond individual stellar catastrophes, there are regions of space where the environment itself is inherently hostile to life. Near the galactic center, stars are packed so closely together that they are separated by distances measured in light weeks or light months, rather than the light years typical of our neighborhood. In these dense stellar environments, close encounters between stars are common, and planetary systems can be disrupted by passing stars, sending planets careening out of their orbits or plunging into their parent stars. The intense radiation from millions of closely packed stars would make the development of complex life difficult or impossible on any planets that manage to maintain stable orbits. The galactic center is also home to our galaxy's supermassive black hole, and while Sagittarius A Times is currently quiet, there is evidence that it has been much more active in the past, releasing bursts of radiation and energetic particles that would flood the inner regions of the galaxy. Some regions of the galaxy are filled with massive molecular clouds, vast structures of gas and dust stretching across dozens or hundreds of light years. Within these clouds, new stars are being born, and the most massive of these young stars live fast and violent lives. They emit powerful stellar winds and intense ultraviolet radiation that heat and ionize the surrounding gas, creating bubbles of hot plasma that can expand to hundreds of light years across. When multiple massive stars form in the same region, as they often do, they create what is called an OB association, a group of hot, luminous stars that collectively flood their surroundings with ultraviolet light and energetic particles. These regions are beautiful when viewed from a safe distance, glowing with the characteristic pink-red light of ionized hydrogen. But up close, they would be extraordinarily dangerous, with radiation levels high enough to strip away planetary atmospheres and sterilize surfaces. The universe also contains structures on even larger scales that pose conceptual, if not immediate, physical threats. Cosmic voids are immense regions of space, hundreds of millions of light years across, that contain very few galaxies. These voids are not completely empty, but they are vastly underdense compared to the average distribution of matter in the universe. Between the voids lie filaments and walls of galaxies, creating a cosmic web structure that extends across the observable universe. While voids themselves are not directly dangerous, they represent regions where a civilization would face extraordinary isolation. A galaxy within a void would see far fewer galaxies in its sky, and the distances to neighboring galaxies would be so vast that intergalactic travel or communication would be even more prohibitively difficult than it already is. A sufficiently advanced civilization in a void galaxy might look out at the universe and conclude they were alone, unable to detect the distant galaxies beyond their cosmic desert. There are regions of space where galaxy clusters collide, creating some of the most energetic events in the universe since the Big Bang itself. When two massive galaxy clusters, each containing thousands of galaxies and trillions of solar masses of material, collide, the result is a cosmic train wreck of staggering proportions. The galaxies themselves mostly pass through each other, as the distances between stars within galaxies are so vast that direct collisions between stars are rare. But the hot gas that fills the space between galaxies in a cluster does collide, creating shock waves and heating the gas to temperatures of hundreds of millions of degrees. These collisions release energy equivalent to millions of supernovae, though spread out over millions of years. The X-ray emission from colliding clusters can be detected across billions of light years of space. The collision also affects the dark matter halos of the clusters, which pass through each other just like the galaxies, providing some of the best evidence we have for the existence of dark matter. A planet in a galaxy within one of these colliding clusters would face a hostile environment. The increased density of galaxies would raise the probability of close encounters, and the intense X-ray background from the heated intergalactic gas would add to the radiation environment. The gravitational perturbations from the collision could also trigger increased star formation and feed the supermassive black holes at the centers of galaxies, creating more quasars and active galactic nuclei that would further increase the radiation levels. The universe contains phenomena that operate on timescales both unimaginably brief and incomprehensibly long, each presenting its own form of cosmic dread. Consider the fate of stars, not as individual events, but as an inevitable progression that will claim every single luminous object in the cosmos. Every star that shines today will eventually exhaust its fuel. The smallest red dwarf stars will burn for trillions of years, far longer than the current age of the universe, but even they will eventually fade. When the last star dies, the universe will enter what cosmologists call the degenerate era, a time when the only remaining stellar remnants will be white dwarfs, neutron stars, and black holes, along with the cold, dark remains of planets and other objects that never achieved fusion. In this distant future, tens of trillions of years from now, the universe will be a profoundly different place than it is today. Galaxies will have collided and merged, forming enormous elliptical galaxies containing the remnants of trillions of stars. But these galaxies will be dark, their stars long dead, their only illumination coming from the occasional flare, as a white dwarf accretes matter from a companion, or from the faint glow of Hawking radiation, from evaporating black holes. Over even longer timescales, measured in numbers so large they defy comprehension, the very protons and neutrons that make up normal matter may themselves decay. While this has never been observed and remains theoretical, many extensions to the standard model of particle physics predict that protons are not ultimately stable. If protons do decay, then on timescales of perhaps 10 to the 34th power years or longer, all normal matter will eventually disintegrate into lighter particles and radiation. The white dwarfs and neutron stars, the remnants of dead stars, will slowly evaporate, leaving behind only black holes and a thin fog of elementary particles. Eventually, even the black holes will evaporate through Hawking radiation. The timescale for this is almost beyond conception. A solar mass black hole will take about 10 to the 67th power years to evaporate completely. A supermassive black hole, containing a billion solar masses, will take 10 to the 94th power years. These numbers are so large that they make the current age of the universe, a mere 14 billion years, seem like the briefest instant in comparison. When the last black hole evaporates, the universe will enter what is called the dark era, a time when the only remaining entities will be elementary particles, photons, and possibly exotic particles we have not yet discovered, all spread across an ever-expanding space-time that has grown cold and dark. The temperature of the universe will approach absolute zero, and the density of matter will become so low that the average distance between particles will be measured in light years or more. This heat death of the universe represents a different kind of cosmic horror than the violent phenomena we have discussed. It is the terror of ultimate dissolution, the final triumph of entropy over order, structure, and complexity. In this far future, not only will life be impossible, but the very building blocks from which life could potentially arise will have ceased to exist in any meaningful form. But the expansion of the universe itself presents immediate concerns that make our cosmic environment precarious. Observations over the past few decades have revealed that the expansion of the universe is not just continuing, but accelerating. This acceleration is attributed to something called dark energy, a mysterious component that appears to make up about 68% of the total energy content of the universe. We do not know what dark energy is. We can observe its effects on the expansion of the universe, but its fundamental nature remains one of the deepest mysteries in physics. Dark energy could take several forms, and some of these possibilities are more disturbing than others. If dark energy is truly constant throughout space and time, as represented by what physicists call the cosmological constant, then the universe will continue expanding forever at an accelerating rate. Distant galaxies will eventually recede from us faster than the speed of light, not because they are moving through space faster than light, but because the space between us and them is expanding so rapidly that light can never bridge the gap. In this scenario, over the course of trillions of years, all galaxies outside our local group will disappear beyond what is called the cosmic event horizon. Future astronomers, in the far distant future, if any exist, will look out at the universe and see only the stars of their own galaxy, and perhaps the merged remnant of the Milky Way and Andromeda. They will have no evidence that billions of other galaxies ever existed. The universe will appear to them as a small island of matter in an infinite dark ocean of expanding space. But there are other possibilities for dark energy that are far more alarming. If dark energy is not constant but instead increases over time, the acceleration of the universe's expansion will become more and more extreme. In the most dramatic scenario, called the Big Rip, the acceleration becomes so strong that eventually even the fundamental forces holding matter together are overcome by the expansion of space. In a Big Rip scenario, the universe would end not with a whimper, but with a catastrophic shredding of all structure. First, galaxy clusters would be torn apart as the space between galaxies expanded faster than gravity could hold them together. Then individual galaxies would be disrupted, their stars flung apart into the void. Solar systems would be next, planets ripped away from their stars and sent careening through space. Eventually, the expansion would become so violent that planets themselves would be torn apart, then molecules, then atoms, and finally, even atomic nuclei would be shredded, as the fundamental forces of nature were overwhelmed by the exponentially accelerating expansion. The timescale for a Big Rip depends on the specific properties of dark energy, but some models place it as soon as 22 billion years in the future, less than twice the current age of the universe. Other models place it much further in the future, or suggest it may not happen at all. The truth is that we simply do not understand dark energy well enough to predict with confidence what the ultimate fate of the universe will be. Another possibility is that what we call dark energy is not a constant property of space, but rather a field, similar to other quantum fields that permeate the universe. If this is the case, the field could potentially change its value over time, or vary from place to place in space. Some theories suggest that this field, called quintessence by some physicists, could even decay to a lower energy state, an event that would have catastrophic consequences for everything in the universe. If the dark energy field is not in its lowest possible energy state, there exists the theoretical possibility of a phenomenon called vacuum decay. In this scenario, a small region of space spontaneously transitions to a lower energy vacuum state. This transition would create a bubble of true vacuum, expanding at the speed of light, converting the false vacuum of our current universe into the true vacuum as it grew. Inside this bubble, the laws of physics, as we know them, would be different. The fundamental constants of nature, such as the masses of elementary particles and the strengths of the fundamental forces, could have different values. In most scenarios of vacuum decay, the new laws of physics inside the bubble would not permit atoms as we know them to exist. The new values of the fundamental constants would be incompatible with the existence of stable matter. As the bubble expanded at the speed of light, everything it encountered would be instantly destroyed, converted into particles and fields governed by the new physics, likely unable to form stable structures of any kind. The terrifying aspect of vacuum decay is that we would have no warning. The bubble would approach at the speed of light, and light itself cannot outrun the bubble to bring us news of its approach. One moment, the universe would be as it is, and the next moment, without any warning at all, everything would be annihilated and replaced by a universe with different laws of physics. Some physicists have calculated that if vacuum decay is possible, the presence of high-energy processes in the early universe or near black holes should have already triggered it. The fact that we exist might be evidence that vacuum decay is not actually possible, or that our current vacuum state is stable, but we cannot be certain. The universe also contains threats that emerge from the quantum nature of reality itself. Quantum mechanics tells us that at the smallest scales, the universe is inherently uncertain and probabilistic. Particles can exist in superpositions of states, being in multiple configurations simultaneously until they are observed or interact with their environment. Empty space is not truly empty, but filled with quantum fluctuations, where particle-antiparticle pairs constantly appear and annihilate. In most circumstances, these quantum effects are negligible on human scales and timescales. But quantum mechanics permits events that are extraordinarily improbable, but not strictly impossible. For instance, quantum tunneling allows particles to pass through barriers that classical physics would consider impenetrable. An electron can tunnel through an energy barrier that it does not have enough energy to surmount through normal means. Extended to macroscopic objects, quantum mechanics suggests that it is theoretically possible, though absurdly improbable, for an object to spontaneously tunnel through a barrier or even to undergo spontaneous rearrangement. You could, in principle, quantum tunnel through a wall. The probability of this happening is so vanishingly small that it will never occur even once in the lifetime of the universe. But it is not zero. More disturbingly, the quantum vacuum itself might be unstable in ways we have not yet discovered. The vacuum is not the absence of everything, but rather the lowest energy state of quantum fields. These fields can have fluctuations, and in rare cases, these fluctuations can be large enough to have macroscopic effects. In the early universe, quantum fluctuations in the inflation field are thought to have been stretched to cosmic scales, becoming the seeds from which galaxies and large-scale structures eventually formed. But quantum fluctuations could also, in principle, create pockets of space where the properties of the vacuum are drastically different from what we observe. Some theories suggest that our universe might be just one bubble in an eternally inflating multiverse, where different bubbles have different properties, different laws of physics, and different values of fundamental constants. The boundaries between these bubbles, if they exist, and if bubbles can collide, would be regions of unimaginable violence where different physical laws meet. If our bubble of space-time were to collide with another bubble in this hypothetical multiverse, the collision would create a boundary region where the laws of physics were in conflict. This boundary would expand at the speed of light, and everything it encountered would be subject to physical laws that were some hybrid or transition between the two different sets of laws governing each bubble. The result would likely be the destruction of all complex structures, as the finely tuned constants of nature that allow atoms, chemistry, and life to exist would be disrupted. There are even more exotic threats that emerge from speculative physics. Some theories suggest the possibility of strange matter, a hypothetical form of quark matter that could be more stable than ordinary atomic matter. Quarks are the fundamental particles that make up protons and neutrons. In normal matter, quarks are confined within these particles by the strong nuclear force. But at extremely high densities, such as those found in the cores of neutron stars, quarks might break free from their confinement and exist in a state called quark matter. Strange matter is a specific type of quark matter that includes strange quarks, in addition to the up and down quarks found in normal matter. Some theories suggest that strange matter could be more stable than ordinary matter. If this is true, then contact between strange matter and normal matter would convert the normal matter into strange matter. This conversion would release energy and would be self-sustaining, as the newly created strange matter would convert more normal matter, and so on. A single strange matter nugget, perhaps created in a neutron star collision, or in the core of a collapsing massive star, could theoretically convert an entire planet, star, or even galaxy into strange matter. This is called an Ice-9 scenario, named after the fictional substance in Kurt Vonnegut's novel that converted all water it touched into a room-temperature solid. A strange matter disaster would spread at a significant fraction of the speed of light, converting everything in its path. Fortunately, the existence of stable strange matter remains purely theoretical, and most physicists consider it unlikely. The fact that neutron stars exist and appear to be stable suggests that strange matter, if it exists at all, is not more stable than ordinary matter under the conditions we can observe. But the possibility cannot be entirely ruled out, and it represents another entry in the catalog of potential cosmic catastrophes. The universe operates on principles that, despite our centuries of scientific progress, we still do not fully understand. Dark matter makes up about 27% of the universe's energy content, yet we do not know what it is. We have inferred its existence from its gravitational effects on galaxies, galaxy clusters, and the large-scale structure of the universe. But despite decades of searching, we have not directly detected a dark matter particle. Dark matter could be composed of weakly interacting massive particles, or WIMPs, that barely interact with normal matter, except through gravity. It could be made of axions, hypothetical particles predicted by some extensions to the standard model of particle physics. It could be primordial black holes formed in the early universe. Or it could be something entirely different, a form of matter or a modification to gravity that we have not yet imagined. The uncertainty about dark matter's nature means we cannot predict how it might affect us in ways beyond its gravitational influence. If dark matter particles are passing through Earth constantly, as many theories suggest, they could potentially interact with normal matter in rare and unexpected ways. Some theories propose that dark matter could decay or annihilate, releasing energy in the form of particles or radiation. If this occurs near Earth or within the solar system in sufficient quantities, it could have observable effects. More speculatively, some theories suggest that dark matter could form structures analogous to those formed by normal matter. Dark matter stars, planets, or even black holes could exist, invisible to our telescopes, but still exerting gravitational influence. The solar system could be passing through a concentration of dark matter, or a dark matter object could be orbiting the sun alongside the visible planets, its presence revealed only through subtle gravitational perturbations. Beyond the threats posed by known or theorized phenomena, the universe may contain dangers we have not yet conceived of, because we lack the physics to understand them. Our current theories of physics, quantum mechanics, and general relativity are extraordinarily successful at describing the universe at the scales we can observe and measure. But these two theories are fundamentally incompatible with each other. Quantum mechanics describes the world of the very small, while general relativity describes gravity and spacetime. At the interface between these two domains, in places where quantum effects and strong gravity both matter, our theories break down. The singularities at the centers of black holes represent one such place. Another is the initial singularity of the Big Bang, the moment when the entire observable universe was compressed into an infinitesimal point. To understand what happens at these extremes, we need a theory of quantum gravity, a framework that can describe how spacetime itself behaves at quantum scales. Despite decades of effort by theoretical physicists, we do not yet have a confirmed theory of quantum gravity. String theory, loop quantum gravity, and various other approaches have been proposed, but none have been experimentally verified. This means that at the most extreme conditions in the universe, we are operating in a regime where our understanding is incomplete, at best, and potentially entirely wrong. There could be phenomena occurring at these extremes that we cannot predict because we lack the theoretical framework to even formulate the relevant questions. The Planck scale, at distances of about 10 to the minus 35 meters, and energies of about 10 to the 19 billion electron volts, represents the frontier beyond which our current physics cannot go. At this scale, quantum fluctuations in spacetime itself become significant. Space and time might not be continuous, but rather grainy or foamy, with the structure of spacetime constantly fluctuating. What happens at the Planck scale is anyone's guess, and it is possible that phenomena occurring at these tiny distances could have macroscopic effects that we have not yet discovered. Some speculative theories propose the existence of extra dimensions of space beyond the three we experience. String theory, for instance, requires the existence of additional spatial dimensions, perhaps 6 or 7 of them, curled up so small that we cannot detect them directly. These extra dimensions could potentially harbor their own forms of matter and energy, their own physical laws, and perhaps even their own structures, analogous to particles, atoms, or more complex systems. If extra dimensions exist, there could be phenomena occurring in those dimensions that affect our three-dimensional world in ways we do not understand. Gravity, for instance, might propagate through extra dimensions, which could explain why it is so much weaker than the other fundamental forces. Some theories suggest that what we perceive as dark matter and dark energy might actually be effects of matter or fields existing in extra dimensions, their influence on our dimensions manifested only through gravity. There is also the possibility that our universe could be a membrane, or brain, floating in a higher dimensional space with other brains nearby. Collisions between brains have been proposed as possible mechanisms for cosmic events, including potentially even the Big Bang itself. If brains can collide, and if our universe is one brain among many, then a collision with another brain would be a cataclysm beyond comprehension, potentially destroying and recreating the entire universe in an instant. The existence of the universe itself poses deep questions that venture into the territory of cosmic dread. Why does anything exist at all? Why is there something rather than nothing? The universe began in the Big Bang, approximately 14 billion years ago, expanding from an extremely hot, dense state. But what caused the Big Bang? What came before it, if anything? These questions push at the boundaries of physics and venture into philosophy and metaphysics. Some cosmological models suggest that the Big Bang was not the absolute beginning, but rather a transition from a previous state. Cyclical models propose that the universe undergoes endless cycles of expansion and contraction. Each Big Bang followed billions or trillions of years later by a big crunch, which then leads to another Big Bang. In these models, our universe is just one cycle in an eternal sequence, with no true beginning and no final end, just endless repetition. Other models suggest that our Big Bang was just one event in an eternally inflating multiverse, where quantum fluctuations in an inflation field cause pockets of space to stop inflating and undergo a Big Bang, creating bubble universes like our own. In this picture, our universe is just one bubble among an infinite number, each potentially with different physical laws, different constants of nature, and different properties. Most of these bubbles might be lifeless, their physics incompatible with the formation of stable atoms or the chemistry necessary for life. The anthropic principle suggests that we should not be surprised to find ourselves in a universe compatible with life, because we could not exist in a universe that was not compatible with life. This reasoning explains why our universe has the specific values of fundamental constants that it does. If they were different, we would not be here to observe them. But this raises the disturbing possibility that our existence is a cosmic accident, a random fluctuation in the parameters of physics that happen to create conditions where complexity in life could arise. Even more disturbing is the Boltzmann brane problem. In an infinite or sufficiently long-lived universe, thermal fluctuations will eventually produce any possible configuration of matter, no matter how improbable. This includes configurations that are conscious observers, brains that spontaneously fluctuate into existence, complete with memories and sensory experiences. In some cosmological scenarios, these Boltzmann brains would vastly outnumber normal observers like us, who evolved through the gradual process of cosmic and biological evolution. If Boltzmann brains are more common than evolved observers, then statistically, you are more likely to be a Boltzmann brain than a real person. Your memories would be false, implanted by random fluctuations, and the universe you perceive around you would not be real but merely a temporary hallucination before the brain that is you dissipates back into chaos. This conclusion is absurd, but it arises from taking certain cosmological models to their logical extremes, and physicists take it seriously as a problem that needs to be resolved. The resolution to the Boltzmann brane problem likely lies in a better understanding of cosmology and the nature of probability in an infinite universe. But the very fact that our theories can lead to such bizarre conclusions suggests that we are still missing something fundamental about the nature of reality. The speed of light represents another kind of cosmic prison. According to special relativity, nothing can travel faster than light, and as objects approach the speed of light, their energy requirements approach infinity. This means that interstellar travel is extraordinarily difficult. Even traveling to the nearest star system, Alpha Centauri, at speeds approaching the speed of light, would require energy expenditures far beyond our current capabilities. The vast distances between stars mean that we are effectively isolated. Even traveling at nearly the speed of light, it would take years to reach even the nearest stars, decades to reach stars a few tens of light years away, and centuries or millennia to cross the galaxy. Communication is similarly constrained. A signal sent to Alpha Centauri would take over 4 years to arrive, and a reply would take another 4 years to return. Conversations across interstellar distances are impossible in any practical sense. This isolation raises the specter of cosmic loneliness. If intelligent life exists elsewhere in the universe, and if the speed of light is truly an insurmountable barrier, then civilizations are condemned to exist in isolated pockets of space, forever unable to meet face to face, limited to exchanging messages across gulfs of time, measured in years, decades, or centuries. The universe could be teeming with intelligent civilizations, and yet each would be alone in their own corner of space, their radio signals growing weaker and more distorted as they spread across light years. The Fermi Paradox asks why, if the universe is so large and has existed for so long, we have not detected any evidence of other intelligent civilizations. There are many potential answers to this question, and some of them are disturbing. Perhaps intelligent life is extraordinarily rare, and we are alone or nearly alone, in the observable universe. Perhaps intelligence is common but tends to destroy itself before it can spread beyond its home planet. Perhaps advanced civilizations deliberately hide their presence. Or perhaps they exist in forms so alien that we do not recognize them as civilizations at all. One particularly dark answer to the Fermi Paradox is the Great Filter hypothesis. This suggests that there is some stage in the development of life or civilization that is extraordinarily difficult to pass through. Most life that begins fails to make it through this filter. If the Great Filter is behind us, in our past, then we are lucky to have made it through, and the universe might be filled with dead planets where life arose but failed to develop intelligence, or where intelligence arose but failed to develop civilization. But if the Great Filter is ahead of us, then our future is bleak. It would mean that something prevents civilizations from surviving long-term or spreading beyond their home worlds. This could be self-destruction through war, environmental collapse, or some other catastrophe. It could be an unavoidable technological disaster, such as the creation of artificial intelligence that turns hostile, or nanotechnology that runs amok. Or it could be some cosmic threat that we have not yet encountered, something that reliably destroys advanced civilizations before they can leave a detectable mark on the universe. The development of advanced technology brings its own existential risks. Nuclear weapons demonstrated that human beings are capable of creating tools that could destroy our own civilization. Climate change shows that we can alter our planet's environment on global scales without intending to. As our technology becomes more powerful, the potential for catastrophic accidents or deliberate misuse increases. Artificial intelligence represents a particularly concerning area of technological development. As AI systems become more capable, there is the potential for them to surpass human intelligence in all domains. If this occurs, and if we have not carefully aligned these systems with human values and goals, the results could be catastrophic. An artificial superintelligence with goals that do not align with human well-being could pursue those goals in ways that are harmful or even fatal to humanity, not out of malice, but simply because human welfare was not part of its optimization criteria. Biotechnology presents another set of risks. The same tools that allow us to cure diseases and engineer crops could be used to create pathogens far more deadly than anything found in nature. Synthetic biology could enable the creation of organisms with capabilities that do not exist in the natural world. Without careful oversight and ethical guidelines, these technologies could produce disasters that would make natural pandemics seem mild by comparison. Even space exploration, our attempt to escape the confines of our home planet and establish ourselves elsewhere in the solar system and beyond, carries risks. If we establish colonies on Mars, or other worlds, those colonies could develop in isolation from Earth, potentially leading to divergent human subspecies or cultures that might come into conflict. The exploitation of space resources could lead to new forms of inequality and conflict. The universe we inhabit is fundamentally indifferent to our existence. The physical laws that govern reality do not care whether life survives or flourishes. Stars will continue to burn and explode, black holes will continue to consume matter, and the universe will continue its expansion, regardless of whether any conscious beings exist to observe it. We are products of cosmic evolution, patterns of matter and energy, that have arranged themselves into forms capable of contemplating their own existence. But we are also temporary. The atoms that make up our bodies were forged in stars and will return to the cosmos when we die. The patterns we create, the civilizations we build, the knowledge we accumulate, all of it exists in a universe that will eventually tear down everything we construct. The second law of thermodynamics tells us that entropy, the measure of disorder in a system, always increases over time in a closed system. The universe as a whole is a closed system, and so entropy is steadily increasing. Order and structure arise locally through the input of energy, but this always comes at the cost of increasing disorder elsewhere. Stars create heavier elements through fusion, organizing simple hydrogen and helium into more complex atoms. But they do so by releasing enormous amounts of energy into space as heat and light, increasing the overall entropy of the universe. Life itself is a process that locally decreases entropy, organizing simple molecules into complex structures like proteins, cells, and organisms. But life can only do this by consuming energy, ultimately derived from sources like the sun. And this energy consumption increases entropy elsewhere. Every living thing is engaged in a constant battle against entropy, maintaining its structure and function by importing energy and exporting waste and heat. When this process stops, when an organism dies, entropy quickly reasserts itself, and the complex structures break down into simpler components. On cosmic timescales, entropy will eventually win. All the structures we see in the universe today, galaxies, stars, planets, all exist temporarily because the universe is still relatively young and far from equilibrium. But over time, the universe will approach a state of maximum entropy, the heat death we discussed earlier, where all energy is evenly distributed and no structures can form or persist. This fate is billions upon billions of years in the future, but it appears to be inevitable given our current understanding of physics. The ultimate fate of the universe, whether it ends in heat death, a big rip, a big crunch, or some other scenario, represents the final cosmic threat. It is not a threat in the sense that it is coming for us soon, or that we could do anything to prevent it. It is a threat in the sense that it reminds us of our fundamental impermanence, that everything we are and everything we create will eventually cease to exist. The universe that gave rise to us will ultimately erase all evidence that we ever existed, returning the matter and energy that briefly formed us back into the cosmic background. Yet despite all these terrors, despite the violence and danger that permeate the universe, despite the ultimate futility implied by the heat death billions of years in our future, we exist here and now. Against all odds, in a universe that seems designed to be hostile to complexity and life, matter has organized itself into patterns that can think, feel, and wonder about their own existence. We are made of star stuff, the products of cosmic evolution, temporary arrangements of atoms that have somehow become capable of contemplating the very cosmos that created them. The universe may be vast, dangerous, and indifferent, but it is also beautiful and awe-inspiring. The same processes that create black holes and supernovae also create stars and planets. The same physics that will eventually lead to heat death also allows for the existence of galaxies, solar systems, and life. We are part of this universe, not separate from it, and our ability to understand even a fraction of its workings is itself a remarkable achievement. The fact that beings like us can exist at all, even temporarily, in a universe filled with so much danger and violence, is perhaps the most extraordinary thing of all.